So this leads to the next part of this lecture, which is discussing in more generality non-negative matrix factorization. So we've already described LDA and made the connection to non-negative matrix factorization. In the remainder of this lecture, I'm going to also discuss two other methods for doing non-negative matrix factorization. And we'll discuss the actual algorithms as well for learning the parameters given some data. So both of these methods are also have the name non-negative matrix factorization. So it's a bit confusing because non-negative matrix factorization is a technique, a general technique, and it's also the name of a set of two different algorithms, which are called, for short, NMF. So when we say non-negative matrix factorization, in general, we're going to mean taking a non-negative matrix and factorizing it into a product of two non-negative matrices. So the general problem of doing that matrix factorization. When we say NMF, which is short for non-negative matrix factorization, we're going to be thinking in general about the two specific algorithms that we're going to discuss in the rest of this class. The intuitions for NMF is similar to the probabilistic matrix factorization problem, PMF, that we discussed in the last lecture. So we can represent them in the same way. In this case, we have an N1 by N2 matrix. Call that X. So this is our matrix of data, where the ijth entry, call that Xij, is a non-negative number. And we're going to assume for this lecture that we have all values in this matrix. So that's important. Last time we had many, many missing values in this matrix. This time we're assuming that we have every value in this matrix. But many, for example, could be equal to 0. But there are no missing measurements here. And we're going to approximate this as a product of these two matrices, one called W and one called H, where if we make a rank K approximation, that means that this is N1 by K, which is the rank, and this is K by N2. And all of the values in these two matrices are also non-negative. So that's the non-negative matrix factorization problem. And our goal now is to learn this matrix factorization. We're going to try to learn the values of these two matrices to have their product approximate the measured data matrix. So notice that last time also the way that we wrote this mathematically was to say that each row here in each column was one vector, and then we represented one particular entry as a dot product of two vectors. In this case, we're not going to write that, so it's purely a notational thing. We're going to say that Xij is equal to a sum over k of Wik times Hkj. So we take Wik for each value of k. We dot multiply it with Hkj, which is each value of this column vector. And then we sum it up. And that represents what our approximation of this element is in the data matrix. There are a few different problems that we could consider using non-negative matrix factorization for. We've already discussed topic modeling. In this case, we have text data where the data matrix contains word term frequencies. What that means is the value Xij, so we have the data matrix X, the value of the ith row in the jth column is a count of the number of times that the ith word I, appears in document J. So in this case, we take this data matrix and we view every column as a different document and every row as a different vocabulary word in our vocabulary. And then the element Xij says how many times did word I appear in document J. So that's the term frequency matrix. And then we factorize that. Another instance of a data modeling problem that uses non-negative matrix factorization is image factorization. In this case, what we do is we take an n by m image, so all the images have to be exactly the same size. We vectorize it by taking the two-dimensional values and putting them all, using the same exact method for each image. We put them all into one long vector of size n times m. And then we put each image along one column of the data matrix X. So for example, if we wanted to factorize images of faces, we would take each face, we would take the two-dimensional image matrix of a face, put it into one vector, and put that along a column of the data matrix, and then factorize that matrix. Other discrete group data work just as well. This is a general technique. What is done is we take sets of features and we quantize them using k-means. And then Xij is going to count how many times cluster I is used by data in group J. So for example, we could have many, many different songs. Each song, in this case, would be like one document. For each song, which is one long audio signal, we extract a set of features that are d-dimensional. Each feature is d-dimensional. And imagine that we have n of these individual features that are spaced out in time across the song. So this could be, for example, something like the spectral information in the signal, where d would be the frequency content, n would index at time slice, and we have a bunch of these features extracted across the song at different time points, saying this is the spectral, the frequency content, which will capture things like guitars and voices and so on. We then quantize all of those features for all the songs together at the same time using k-means clustering, where the k now it corresponds to like the vocabulary, the size of the vocabulary. So we set k. Then every song is now reduced from a set of d-dimensional features to a sequence of indexes of which cluster each of those features was assigned to. And then we histogram that, put that along a column of the matrix X, and factorize it. And that way we can say how songs use the code book, how they cluster across the code book. And so similar songs should use the codes from k-means in a similar way, and so on.